Hello. Previously, I went over some basic math, and today I'll be going over some more intermediate math. First, we'll go over exponents. The notation for exponents is going to be some value and then to the power of another value. This is x to the power of 3, and what you're really doing is repeated multiplication. So this is x multiplied by itself 3 times, so x times x times x. If we want to do it with actual numbers instead of x, here is 3 to the power of 2. This can also be called 3 squared. If you do anything to the power of 2, you can also call it squared. And this is equal to 3 times 3, which would be 9. 4 to the power of 3, this can also be 4 cubed, so anything to the power of 3 can also be cubed. And this would be 4 times 4 times 4, which would be 64. And 5 to the 4th doesn't have any shorthand, but you would just call 5 to the 4th or 5 to the 4th power. 5 times 5 times 5 times 5 gets you to 625. And I would advise just kind of memorizing all of the squares at the very least, from 1 to 10, and here they are. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared 49, 8 squared 64, 9 squared 81, and 10 squared 100. There can also be fractional and negative exponents. So for fractional, x to the 1/2 power can also be said as the square root of x. So this notation is the root, and normally you would have, like for here, this is the x to the 1/3 is the cube root of x. So normally you'd have a number here, but because square root is the most common, if you put nothing, it's just assumed to be the square root. And it's asking what number, when you square it, will be equal to x. And this one is what number, when you cube it, will be equal to x. So here's some examples. So the square root of 4 is 2, because 2 squared would be 4. And here, the cube root of 27 is 3, because 3 cubed would get you to 27. And here's another example. So if you have not just 1 over something, but like 2 over 3, for example, all that means is inside the radical is squared, and then you take the cube root of it. So this is the cube root of 8 squared, or the cube root of 64, which would be equal to 4. So 8 to the 2 over 3 is equal to 4. There's also negative exponents. So if you have a exponent to the negative power, it's the same as taking the reciprocal of x to that positive power. So it just puts it on the other side of the division line. If it's in the numerator, it becomes a denominator. And if it's in the denominator and it has a negative exponent, then it's moved to the numerator. So 1 over x to the negative 1 is just equal to x. And if you have x to the negative 2, it just becomes x squared in the denominator. And if you have fractional, it just becomes square root in the denominator. Here are some examples on how you can distribute exponents. So if you have the quantity xy squared, that's equal to x squared times y squared. And if you have the quantity 4x squared y cubed, all cubed, then that's equal to 64, which is 4 cubed, times x to the 6, which is x squared cubed, times y to the 9th, which is y cubed cubed. Use another example. So if you have 4x cubed times z times root y, all squared, divided by 2x to the negative 1, y squared root z, first you can distribute the squared and square all of these terms. And then you can move things that have a variable in common. So negative x moves up to the numerator and makes this x to the 7th. The y here can cancel with one of the y's here and just leave a 1y in the bottom. And this z, which is really z to the 1/2, can cancel with a z to the 1/2 here, leaving z to the 3/2. And the 16 and the 2 would cancel to become 8. Logarithms, which are very closely related with exponents. If you have an exponent where a to the b is equal to c, that means that log base a of c is equal to b. So if this is true, then this is also true. And if this is true, then this is also true. So the way you would say is, if you see something like this, you'd say log base a of b. For example, log base 2 of 8 is equal to 3, because 2 to the power of 3 gives you 8. Here are some common rules for logs and common logs as well. So log with the base a of a is equal to 1 no matter what a is going to be. So a log with the base, with the argument equal to the base, will always be equal to 1. Another one is if you just see log of a with no base given, it's assumed to be log base 10. This is called the common log. We're in a base 10 system, so the most common one we use is base 10. So just log with no base is assumed to be log base 10. And then there's also natural log, which is another commonly used log, and that's just log with a base of e, which is about 2.718. So the natural log of a is just the log base e of a. And here are some other rules. So if there's addition between logs that have the same bases, that's the same thing, you'll get the same value as multiplication inside the log using that same base. And if there's subtraction outside the logs with the same base, the same as the division inside the log with that base. There's also, if you have an exponent inside the argument, it's the same thing as just multiplying that whatever was the exponent times what you would get for the argument with no exponent. And finally, there's if you have a log base a of b, you can rewrite it as log base c of b divided by log base c of a, where c is just any constant and b is the argument and a is the base. Next, I'll go over some inequalities. So here is equal, not equal, less than, greater than, less than or equal to, greater than or equal to, approximately, and proportionally. So first, equal to, you know this. So if you have x is equal to 0, that means there's just a point here. X is equal to that one point. If we have x is not equal to 0, that means every single point except for x is equal. So all of this and all of this. So from everything but 0 to negative infinity, everything but 0 to positive infinity. If x is less than 0, that means all on the left side, that it can all be what x is equal to, right? So negative 1, negative 2, negative 3. But 0, 1, 2, so anything 0 and above, it can't be equal to. Greater than equal to, the same thing but flipped. So anything above 0, so 1, 2, 3, or 0.1, or anything like that, all the way up to positive infinity, would make this inequality still true. But anything below, anything 0 or below, would make this false. And then there's greater than or equal to, which just includes that point you're looking at. So instead of not including 0 and going here, you are including 0 and going here. And with greater than or equal to, same thing but flipped, you include 0 and everything greater than it. Then approximately, so this isn't usually used with math, but if you're doing approximations, then this is what the symbol you'll use. So it's around 0. You don't know the exact value. And usually you'll use it for very large values. You'll say, oh, it's approximately 700 maybe. Maybe it's between 690 and 710. Finally, proportionally, so two variables can be proportional, which means the constant factor between them will be the same. So for example, if the constant factor between them is 2, if x is 1, then y will be 2. If x is 2, then y will be 4. If x is 3, then y will be 6. So y is always twice as much as x, and they're always proportional. And the same works with negative. So negative 1, negative 2. If x is negative 2, then y will be negative 4. You could also do a half proportion. So if x is 6, then y would be 3. So it just means whatever x is, y has to be a constant factor multiple of that. Here are some extra expressions. First, absolute value, a pretty common one. So the absolute value of negative a is equal to a, and the absolute value of a is equal to a. So it just takes the distance the value is from 0. If it's negative, then it becomes positive. If it's positive, it stays positive. So your answer will always be positive, regardless of if the original one is negative or positive. Next is the floor. So this is essentially just rounding down. So if you have any fractional part that's not a whole number part or non-integer part, then you'll just round down to the next integer. So 0.5 would round down to 0. Negative 0.1 would round down to negative 1. Ceiling, very similar thing, but instead you're just rounding up. So 0.5 rounded up is equal to 1. Negative 3.6 rounded up is equal to negative 3. Next, about some functions. You'll see notation like this, where f of x is equal to x. this says the function of x is equal to this expression, and the expression is just x. Oftentimes, people can also say y is equal to x, and usually that there's an assumed y is equal to f of x in there. So for f of x is equal to x or y is equal to x, this is how it would graph. As x increases, which is the input, so x is the input, and then f of x is the output. So as x increases, the function of x also increases at the same rate. So they increase at the same rate, and they'll go along this line. You can also have multiple inputs. So the function of x and y would be written like this, or multiple outputs. So the function of x with a two-dimensional output would look like this. And if you have multiple inputs and multiple outputs, you'll just combine the two. So the function of x and y is equal to this, which has two completely separate outputs. You could also have inverse functions. So with inverse functions, all you're doing is swapping the inputs and the outputs. There's also composite and piecewise functions. So if you have two functions, f of x and g of x, where f of x is equal to 4x plus 2 and g of x is equal to x squared, then f of x plus g of x is just equal to the expressions added together, just like these functions are. So x squared plus 4x plus 2. If you're dividing the functions, then you're just dividing the expressions. However, if you have composite functions where the one function is kind of nestled inside of the other, so this is the function f of g of x is what you would say. And here, so given the f of x expression, we'll plug g of x into it. So we'll plug x squared into this 4x plus 2, and we'll get 4x squared plus 2. And if we swap the order, so g of f of x, then we'll have this g of x function, and we'll plug the f of x function in for x for g of x. And we'll get 4x plus 2 quantity squared. There's also piecewise functions, which separate the domain into different expressions. So f of x is equal to x when x is less than 0. F of x is equal to x squared when x is greater than or equal to 0 or less than 3. And f of x is equal to 2 minus x when x is greater than or equal to 3. When x is less than 0, you're to the left of the 0 when x is equal to 0, right? And you'll just follow this f of x is equal to x. Then, when you reach 0, then you look at this domain. So we're looking at x squared. So it will follow x squared until it reaches 3. And at 3, it won't quite reach it. And then we'll look at where it is. So here, it would be 3. So we'll plug in 3, starts at -1, and it will continue until positive infinity. Graphing. So usually you'll graph with y equals x or f of x is equal to x. Normally, with just one variable, you can put it on the number line. But with two variables, y or x, or with an independent and dependent variable, then we'll need a perpendicular number line to create the dependence of the two different variables. That's how we get this coordinate grid. So here, y is equal to x or f of x is equal to x. As x increases, y also needs to increase. So this line includes all of the different possible pairs of x and y, or x and f of x, where these equations are true. Here's another given function where you can graph it. So f of x is equal to x squared minus 4. And it would look differently, but these still give you all of the different pairs of x and f of x where this equation is true. Now I'll go over some common terminology used with graphing. First is the slope. The slope is what is the change in y given the change in x. So for this one, as x increases by 1, y also increases by 1. So the ratio between them is just 1 to 1, so 1. But if it was a steeper slope, let's say it was f of x is equal to 2x, then it would extend like this. And the slope would be 2, because every time you move x by 1, you move y by 2. So it rises 2 over 1, or the slope would be 2. And here, the slope actually isn't always constant, because here the slope is negative, because as you increase x, you actually decrease y. And then here, it becomes 0, because it's going completely flat. As you increase x, y isn't changing. And here, as you increase x, y is actually increasing. So some functions have the slope is dependent on the x value. There's also the origin. So the origin of a graph is always at 0, 0. So this point right here or this point right here, where x is equal to 0 and y is equal to 0. There's also the intercepts. So the x-intercepts is everything that when y is equal to 0, because it will cross this line, it's called the x-axis. So anytime a graph intersects with this line, it's called an x-intercept. And there can be multiple, like you see in this case. And the y-intercept is when it intersects the y-axis, or when x is equal to 0. For this, there can only be one, because a function can only have one output for each input. It can't have an ambiguous output. So it can only have one y-intercept in a function. Technically, an equation could have more if you graphed it, but a function will only have one y-intercept. There's also the vertex. This is where the slope changes from positive to negative, or it's also where minimums and maximums are. So here, the vertex is at 0, -4, because that's where it changes from negative to positive. And minimums, maximums. So this would have a minimum at -4, right? Because it never reaches anything below that. And that also, there could also be a maximum if this was flipped, for example. If it was more like that, then there would be a maximum at this value. So y equals 3. And that brings us to domain and range. So domain is all of the possible x values that work in this equation. So for both of these equations, x is completely unrestrained. X can be any value, and the function can be computed and will have an equivalent y value for it. And range is all the possible y values that it could be. So for this one, the y values extend from -infinity all the way to positive infinity. So there's, for every y value, there is an equation that would work. But for this one, as we said, there's a minimum here. So anything below this would not have a y value associated. There is no y value where this would be true. So the range of this function would be -4 to infinity. Finally, end behavior is, we can look and see as the functions get either more and more negative until -infinity, or more and more positive until positive infinity, we can look where the graph will tend to go. Here, as you go to -infinity or positive infinity, you're always going to positive infinity for y. But here, as you're going to -infinity for x, y goes to -infinity. And as you're going to positive infinity for x, y goes to positive infinity. So you can look at the end behavior to see what the graph will look like overall. Now onto interval notation. The main way to use interval notation are the parentheses, the brackets, or the braces. So with parentheses, that means you approach that value but never quite reach it. And with -infinity and positive infinity, you will always use parentheses because you can't ever really reach infinity. So given this -infinity, positive infinity, that tells you you extend from -infinity and positive infinity and all of the values in between. So the entire number line would be this. For 0 to 2, that would be at 0, and this bracket means you include that point. So it would be at 0, and then you would extend to 2, but it wouldn't include 2. So 0 to 2 and everything but 2. So like 1.999 would work. 1.99999, any number that's really, really close to 2, but actually at 2, it wouldn't be on that interval. Finally, with these braces, this just means discrete or distinct values. So this includes 3, 4, and 5, but not anything in between. So only 3, 4, and 5 with these braces. There's also some other notation. So this is a union sign where you can have the union of two intervals. So this interval is -infinity to -3. So that would go here, and it would include this point, like this. And this 2 to infinity would start at 2, not include that point, and extend all the way to positive infinity, like this, with this open circle, meaning not including, but any value infinitely close to it. Then the union of these two sets would just be exactly what you see here. Any number that is in either of these intervals would count as in the union of these intervals as well. There's also intersection with this upside down u. So the intersection of these two intervals can be shown with this upside down u. So this interval, -infinity to 1, would go like that and extend to -infinity and end at 1. And -2 to infinity would start at -2 and extend to infinity. And the intersection is all overlapping values. So all the overlapping values from here and here would be this portion. And that's exactly what the intersection will be. Next, geometry. First, I'll go over some of the lines. So this means just a line. This means a ray, and this means a line segment. So given this geometry, CD, which is this, is an infinitely extending straight line in both directions. So we can denote that CD as this. So this tells us exactly what we see here. The CD is a line that extends infinitely in both directions and straight. CB, with this notation, tells us that CB is a ray that starts at C and extends in the direction of B infinitely. So its origin is at C, and in this direction, it extends infinitely. So this is a ray CB. And then finally, we have a line segment. So AB is a line segment. It starts at A, ends at B, and it does not extend infinitely, and it is a straight line. All three of these would be straight lines, but some are infinitely long, some are infinitely long in one direction but not the other, and some are finite. Next, we can have an arc. So this arc from C to B can be described with this notation, the arc from C to B. It can also be an angle. So if you want to talk about this angle here, that would be the angle ACD. There's other ways to describe angles. So the angle ABC, so this angle, can be described using this notation, ABC. And if you want to talk about a right angle or a perpendicular angle, use this square angle notation. So CDB tells us that this is a right angle or a 90-degree angle, or they're perpendicular. Speaking of perpendicular, here are this is perpendicular, this is parallel, and this is not parallel. So if you want to say that two things are perpendicular, you say AB and BD are perpendicular, and they are. For here, the parallel, you'd say AB is parallel to CD, because they have the same exact direction, and that means they will never cross. And if you say AB is not parallel to CB, that means they don't have the same direction, and they will eventually cross if you extend them. Finally, we have these notations. So this is degree. This is a way to denote a triangle, and this is a way to denote a square. So with degrees, it can tell us about angles. So for example, this angle would be a 90-degree angle. This angle is half of that, so it would be a 45-degree angle. And an angle can range anywhere between 0 and 180, and if you want to extend even further, technically 0 all the way to 360. So 360 degrees is one full turn. A way to describe a triangle, so if you wanted to talk about this triangle right here, you would say the triangle CBD. So all of the vertices of the triangle with this notation describes algebraically that triangle. Same thing with the square. We say square ABCD, the square ABCD. That describes this square with all the vertices. Finally, sequences. So sequences are just ordered lists of numbers. So this sequence, we see 1, 2, 3, 4, 5, 6, 7. The pattern might be pretty obvious. Each number is just one more than the previous one, right? Let's look at this sequence now. So here we have 1, 2, 4, 8, 16, 32. And the pattern, you might be able to see it, is each number is double the one previous. So each number is a common ratio of 2 times the one previous it. So, using what we just said, we can describe these using an equation. A term of a sequence, the nth term of the sequence, can be described with the previous term plus a common difference for this one. So the common difference for this would be 1. And here, the nth term of the sequence is equal to the previous term times the constant ratio. And here, the constant ratio would be 2. But this doesn't completely describe this sequence, because here, this sequence specifically starts at 1, and this doesn't tell us where the sequence would start. So we need to be told what a specific term is. Usually, the best one is the first term. So if we're given the first term, here a of 1, this would be 1, and here a of 1 would also be 1, and this can be stated explicitly what any term is. So the nth term is equal to the first term plus the common difference times the number of terms they get from 1 to the one you're on right now. So for example, if you wanted to find this is the 7th term. And so we do the first term, 1, plus the common difference, 1, times the 7th term minus 1. So 7 minus 1 is 6, times 1, 6. 6 plus 1 gives us 7. So we can find this term. And the common difference could be 2, or 3, or even -1, or something like that, or even a fractional value. Then for this one, this is the explicit formula. This would be the nth term is equal to the first term times the common ratio to the power of the difference between the term you're on right now and the first term. So if we want to find this is the 6th term. So, and we know the first term is 1, so 1 times common ratio 2 to the power of 6 minus 1, 2 to the power of 5 gives us 32. 32 times 1 will be 32. So we can figure out that the 6th term is equal to 32. So these are the what are called recursive formulas. These ones, where you can find a value given the previous value, and these are called explicit formulas, where you don't need the previous value. All you need is a term and the common ratio or difference. And this, where there is a common difference, is called the arithmetic sequence. And this, where there's a common ratio, is called a geometric sequence. Not all sequences need to be arithmetic or geometric. For example, the list of all prime numbers, so 2, 3, 5, 7, 11, that is also a sequence, but it doesn't have a mathematical formula to describe it. So the only way to describe the sequence is to list out all the terms. And sequences can be infinitely long or finite. So a sequence like 4, 7, 8, that's a sequence. It might be hard to describe using mathematically. Or a infinitely sequence like one of these where you could make it, oh, the next one is 8, 9, 10, 11, so on. This would be 64, 128, and so on. So sequences don't necessarily need to have a recursive or explicit formula. And sequences can also be finite or infinite. All that matters is that it is an ordered list. And something else is it needs to have discrete values. So a of n is a of 1 or a of 2 or a of 3. But you can't have a of 1.5 or even a of 0 or a of -1. A sequence can only have what are called natural number terms. So 1, 2, 3, 4, 5 up until infinity. But it can't be any fractional 0 or negative value. All right, so that is all intermediate math that you may need. And thank you for watching.